Thank you, and thank you for that kind introduction and for all of the hospitality I've had this week here in Norway. It is my first visit to Norway, and it's a wonderful country. So I'll be telling you about the James Webb Space Telescope. It's a 6.6 meter diameter space telescope. It's the successor to the Hubble Space Telescope and NASA's previous infrared mission, the Spitzer Space Telescope. It works in the visible light to an infrared region from 0.6 microns, which is gold-colored light, and you'll find out why it's gold, out to 28 microns, which is sort of heat radiation from room temperature objects. It is the first time that NASA has used deployed optics, moving mirrors out in space for this type of telescope. It is passively cooled. Zero, that's 55 Kelvin, and in fact that's the warmest part of Webb is 55. It goes all the way down to 6 degrees above absolute zero in one of the instruments. It was launched on Christmas Day 2021. Designed from the very beginning to work well with every other telescope, both the missions that we have in space and the large ground-based telescopes working on the ground. It is an international project by NASA, the Canadian Space Agency, and the European Space Agency. In all, there were 14 countries that contributed hardware to Webb, and Norway participates as a member of the European Space Agency. The lead is NASA's Goddard Space Flight Center, just outside of Washington, D.C., where I work. The industrial partners are Northrop Grumman Aerospace Systems and Ball Aerospace, and the operations is done at the Space Telescope Science Institute, which also operates Hubble from the campus of Johns Hopkins University. This is called the Hubble Ultra Deep Field. Until a year ago, July, it was the faintest picture that humanity had ever taken. With the Hubble Space Telescope, over a month of staring at the same part of the sky and almost a full year of follow-up observations with Hubble going back to study individual objects in this field and in the surrounding area. We do deep fields in order to look backwards in time, to take advantage of the fact that light takes time to travel from distant objects to our telescopes. And sometimes, if we are looking at the very furthest reaches of what our telescopes can do, that is most of the history of the universe. The universe is 13.8 billion years old, and Hubble was able, in this picture, to reach back to about 0.8 billion or 800 million years after the Big Bang to see light that has been traveling for 13 billion years. We can look backwards in time, kind of like an archaeologist digging deeper and deeper to layers and seeing further into the past. And when we do this, when we look at the faintest, most distant galaxies in this picture, we were a little bit surprised to discover that we were not finding the first galaxies that formed in the early universe in this field, because some of these most distant galaxies that we can see with Hubble are in fact several hundred million years old already when they are emitting their light within the first billion years after the Big Bang. So that meant we needed to go beyond Hubble to find the initial conditions for galaxy formation and evolution, the first things that formed out of the pristine material that came from the Big Bang. So we needed a telescope that was bigger than Hubble, because to find things that are further away, you need to collect more light. You need to gather that light in a larger telescope. Webb is 6.6 meters in a hexagonal pattern from flat to flat on the outer reaches, whereas Hubble has a circular telescope that is 2.4 meters. In all, there's 6.25 times more collecting area, more light at the same time. But as the light from these very distant galaxies is traveling through the expanding universe, the expansion of space-time is stretching out the wavelengths of the light. Similar to a Doppler shift, When a train is coming towards you, it sounds higher pitched. When it's going away, it's lower pitched. The sound waves are stretched out. That happens with light when things are traveling through the expanding universe. And so the light that was emitted as ultraviolet or visible light by these galaxies has been stretched out and moved to the infrared. So we needed an infrared telescope, something that could work at longer wavelengths than Hubble can work. And to do that, we need a cold telescope because anything with a temperature emits infrared light. And the colder the temperature, the less of that infrared light can get in the way of our observations. Hubble is kept at room temperature by means of onboard heaters. It goes in and out of the sunlight every 90 minutes as it goes around the Earth. But Webb is situated behind a 5-layer tennis court-sized plastic sun shield. This sun shield protects the Webb, the telescope, from the sunlight. As we'll see in a minute, it also protects the telescope from light reflected from the Earth. And this allows the telescope to emit all of its heat out into deep space and cool down to these very cold cryogenic temperatures. And finally, we had to put it in a different orbit than Hubble. Hubble is at 600 kilometers above the surface of the Earth. It's the highest that the space shuttle could fly. But that's called low Earth orbit. It goes around the Earth every 90 minutes, and it goes between the Earth and the sun. So the daylight side of the Earth is shining on the telescope from one direction, the sunlight from the other, heating it up. In order to cool Webb down to the cryogenic temperatures, we needed to put it 1.5 million kilometers away in a special orbit called the second Lagrange point. It's in a halo orbit around that point, but the L2 point stays lined up with the Earth and the sun. As the Earth goes around the sun once per year, the L2 point goes around the Earth once per year, and exactly lines up so that the sun shield is protecting the telescope from the sunlight, from the Earth light, and from the moon. This is a family portrait of our 4 cameras on board the telescope. They sit behind the telescope. We have the near-infrared camera, works from 0.6 to 5 microns wavelength. It takes many of the pictures that you've seen or that you'll see today. We have the near-infrared spectrograph, which takes the light from the objects and stretches it out to all of its constituent wavelengths. This way we can see the signatures of the elements in the light that we're receiving. This will be, you'll see a lot of spectra. I'll show you a lot of spectra that tell us about the objects that we're seeing in the pictures. As one astronomer said, spectroscopy puts the fizz in astrophysics, tells us about the objects. The near-infrared spectrograph is a European Space Agency contribution. Our Canadian instrument is a guider that locks onto target stars and maintains the pointing of the telescope. And then there's an additional specialized scientific capability that is designed to study distant galaxies and planets around other stars. And then finally, our mid-infrared instrument looks at the longest wavelengths from 5 to 28 microns and takes both imaging and spectroscopy. And that was a joint project of a consortium of European countries managed by the European Space Agency with the Jet Propulsion Laboratories, which provided the detectors and the cooling system. That is the instrument that uses a closed-cycle helium-based gaseous helium refrigerator to go down to 6 degrees above absolute zero, or 6 Kelvin. Assembly of the primary mirror. We have 18 hexagonal mirror segments, each 1.3 meters across. The mirror segments are made of beryllium, atomic element number 4. It's a very lightweight, stiff metal, and in fact, we took out most of the material and left a honeycomb structure on the back and a very highly polished surface on the front. The advantage of beryllium for a space telescope is that it has a very low coefficient of thermal expansion at cryogenic temperatures, so the temperature difference across the face of the Webb mirror is 20 degrees Kelvin, but we did not have to take that into account while making the figure of the mirror. Big advantage. The other aspect of the telescope, as you'll see, is the two side wings are folded back for launch and deployed in space. When we had the telescope fully assembled in the clean room at Goddard, this is the largest Class 10,000 clean room in the world, and we took a picture, the photographer took a picture of the Webb mirror with the NASA logo on the back wall reflected in the mirror. One thing that you can see right away is that this is not a flat mirror like you have in your restroom. This is a curved mirror. It focuses the light. Light hits the primary mirror, bounces off the secondary, and goes through the tube in the center of the telescope to the instruments. There are some of the very proud technicians who assembled the mirror pictured. I'm not in this picture. They don't let the scientists go in the clean room anywhere near the spaceflight hardware. We just have to think about it and let the highly skilled technicians and engineers put the telescope together. But you can see on the back wall that there is a, let's see, right here, there's a viewing window. And there was a time when the telescope was pointed at the viewing window, and I was able to take the coolest selfie I will ever take in my life of myself reflected in the 6.5 gold-coated mirror for Webb. Once the telescope was assembled with the instruments on the back, we took it to a vacuum chamber at the Johnson Space Center in Houston, Texas. This vacuum chamber is 12 meters in diameter and 35 meters high. It is one of the biggest in the world. And this vacuum chamber was built for the Apollo astronauts to practice walking on the surface of the moon in their spacesuits. So human astronauts went inside this vacuum chamber, they pumped out all the air, and they practiced in their spacesuits. When the Webb project took this over, we took out the simulated lunar surface, cleaned up all of the lunar dust, and installed a helium shroud to bring the temperature down to the operating temperature of Webb. After that test, we took it to Los Angeles to the Northrop Grumman facility, where they had assembled this tennis court-sized sun shield and installed the telescope and the cameras onto the spacecraft. The spacecraft maintains position in the orbit using rocket thrusters and also provides communication, sending the data down to Earth. After the assembly of the telescope onto the spacecraft, we did a test of the deployment of the sun shield. Now, this had to happen in space completely autonomously. On the ground, we needed to support it on a table against gravity, but of course, in the actual deployment, it was done in zero gravity, and we didn't need that table. That test was successful. We folded it up, ready for launch, and you can see that it's launched on its side here with the two side wings of the telescope folded back, and the sun shield is wrapped around the telescope. We then put it on a boat, the MN Colibri, and sent it through the Panama Canal. In the lower left, you can see one of the webcams from the Panama Canal. It's really cool. You can look anytime you want and see the ships passing through the canal. But this was Webb going through one of the three locks of the Panama Canal to Kourou, French Guiana, South America. That is where the Ariane 5 rocket is launched from. The European Space Agency launches from French Guiana. And the picture on the right shows our last human interaction with the Webb telescope before it was sealed into the rocket shroud. We now have the launch.
10, 9, 8, 7, 6, 5, 4, 3, 2, unité, top.
And we have engine start. And liftoff. Décollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe.
It was a great Christmas present for those of us who had worked on this project for more than 20 years to see such a perfect launch go off. It was part of our European contribution, the Ariane 5 launch. I think it was the second to last launch of the Ariane 5, and after that, they're now launching the Ariane 6. So when Webb separated from the upper stage of the rocket, there was a camera that got our last high-resolution view of Webb. Now, I will say you can still see Webb if you've got a large amateur telescope, but you see it just as a point source reflecting its light from the sun shield back to Earth. Sort of a typical university-based telescope can detect Webb. It's about 10 times fainter than Pluto. So if you ever get a chance to work with amateur astronomers, see if you can find it. Overhead at midnight at the L2 point. After the separation, one of the things that was very exciting to see was the deployment of the solar panel that provided power for the mission. We actually only had 7 hours to get that solar panel deployed, or we would run out of power and that would be the end of the mission. We could no longer control it. So to see that deploy 90 seconds after separation was very exciting. In the next 2 weeks after launch, as it was heading out its 1.5 million kilometer journey, we did all of the major deployments. There are a total of 50 major deployments, and everything worked successfully. 178 release mechanisms, they all worked. Solar panel, you just saw it come out. It's providing nominal power. We need about 1 kilowatt, 1,000 watts, and the solar panel provides 3 kilowatts, which gives us plenty of margin. The high-gain antenna is deployed and pointed at the Earth, and we send data down once or twice a day through the Deep Space Network. We had mid-course corrections. These are firing the rockets to get it right into position for its launch, for its orbit. But because the launch worked so well and the mid-course corrections went right on time, we actually have fuel left to maintain the orbit for more than 20 years. We also use fuel to manage the angular momentum of the observatory in space. So look forward to a 20-year lifetime of Webb data. The next major deployment was the sun shield. You saw the test on the ground, but now we have a computer animation of the deployment in space. This included 140 of those release mechanisms. If any one of them had stuck, it would have ripped the sun shield and we would have a warm telescope. But they all worked. 70 hinge assemblies, 8 deployment motors, 400 pulleys, 90 cables totaling 400 meters, and everything was successfully deployed. You can see the separation. They're about a half a meter in between each. And of course, this is in vacuum, so it works like a vacuum flask. The light escapes between the heat escapes between the layers, and each layer is successively colder. Final major deployment was the telescope. We have the secondary mirror folding out on its spider, an infrared radiator, and the 2 side wings of the primary mirror. We then followed this with a 3-month-long process to align these mirrors to a fraction of a wavelength. Now, when I'm in the United States, the way I describe this is that if the Webb mirror were the size of the United States, then each of our mirror segments would be the size of the state of Texas, and we would need to line up the state of Texas to Louisiana, Oklahoma, and New Mexico to an accuracy of about 2 centimeters. That's how accurate we had to do to reach the 150 nanometer accuracy for the mirror. But everything worked fine, and I'm going to move on now to some of the science that we got in the first year of Webb. Way back 20 years ago, the scientists got together in a committee, and we wrote down what the science goals would be for Webb. And we organized those science goals around 4 science themes: finding the first galaxies that formed in the early universe, and learning how those galaxies reionized the hydrogen between the galaxies. Studying the evolution of galaxies, how galaxies change from those first small pieces to be the big, bright galaxies like our own Milky Way that we live in. Formation of stars and their planetary systems within the Milky Way galaxy, and studying exoplanets and planets in our outer solar system and looking for the conditions for life. How do planets form in such a way that might eventually lead to planets with life on them? With our first data from Webb that came out last July, we have been addressing all 4 of those science themes. So finding the first galaxies with deep galaxy surveys, I'll show you some of those. Evolution of galaxies as galaxies interact with each other and merge together, the formation of stars and planets in star-forming regions in our own galaxy, and the study of exoplanets and the organic chemistry that we're seeing in the atmospheres of those exoplanets and in the outer solar system. But these were the science themes that we used to organize the science for the mission 20 years ago. We are doing a great job at addressing those science themes, but I'm going to tell you a bit about some of the things, the themes that have emerged within the last year. So starting again, this last July was the deepest picture that humanity had taken at that point. I think we've kind of broken the record one more time, but we're continuing to do very long exposures with Webb. This is a lensing galaxy cluster that allows us to use the gravity of the cluster of galaxies itself to focus the light of galaxies that are even further back, allow us to, with the magnification, we can actually see further and get much better data on some of these very distant galaxies. But we have a series of galaxy survey fields, and we do this to find the statistics of how galaxies form and how they change over time. This is one project that personally I'm a member of the science team. It's a science team of about 120 of us working together on this project. It's called the Cosmic Evolution Early Release Science Program. And one of the things I want to show you is this video of zooming in this image as I think the video should be running. Let's try one more time. There we go. Okay, so we are zooming through this image, and it kind of illustrates how we can look backwards in time. As we go further and further away, we're seeing light that was emitted earlier and earlier in the history of the universe, till we get to the very most distant sources where we're looking for the first galaxies that formed in the early universe. Now, how can we tell that when we see that? So galaxies are made up of populations of stars, of course, and the first stars that formed after the Big Bang only had the elements that came from the Big Bang. The Big Bang itself produced about 80% hydrogen, about 20% helium, and only very small traces of elements 3 and 4, lithium and beryllium. Nothing heavier than that. No carbon, no oxygen, nothing to make water and people and planets and that kind of thing. So those elements all formed within stars. So those first generation stars are made up of only hydrogen and helium. We call those population 3 because we're looking backwards. Population 2 stars are stars that start to have the heavier elements, oxygen, carbon, and so forth, but not nearly as much of those elements as the population 1 stars, like our own sun. Our sun is essentially a 3rd generation star, or a population 1, and has much more of those metals. So the process of star formation is that stars form, some of them, the biggest ones, blow up and distribute those elements that formed in their center to the surrounding area. The next generation of stars will have those heavier elements. So that was the zoom in we just had, and we're starting to look with the spectrograph at some of those very distant galaxies. And we have here the current record holder. It's at a redshift of 13. That means the light has been stretched by the expansion of the universe by a factor of 13, going all the way from the ultraviolet to the infrared. And so this light was emitted at 325 million years after the Big Bang. We're looking backwards in time 13.5 billion years at that galaxy. But this is a low-resolution spectra, and we did not see any emission lines in that spectra. Here's several other low-resolution spectra. So we needed to go back and start to study some of these objects, again, with higher resolution spectra, where we can start to see lines and look for the heavier elements. This is a galaxy that's at a redshift of 10.6, or 430 million years after the Big Bang. Still very early on, but we are starting to see evidence not only of hydrogen, the Lyman alpha line, but also nitrogen. I'm supposed to use the pointer for the people online. So Lyman alpha is hydrogen, nitrogen, carbon, oxygen, another line of nitrogen. We have magnesium, neon. This is a beautiful spectrum, kind of astounding to see something this faint this far away with this quality of data. But this is clearly a population 2 galaxy. It's already been through the first generation of stars. It's not just hydrogen and helium. So the first thought, of course, is that we need to look still further to see the first generation of galaxies. But then this paper came out recently, and this is what we are looking for. This is a population, this looks like it fits a population 3. We're only seeing this helium line. And when we plot that helium line, when the people who did this plot the helium line, it's the yellow circles up at the top, and they're compared to the blue are the population 3 galaxy models, but the gray and purple stars are population 2. So this looks a lot like a population 3 galaxy. And I thought, wow, when I first saw that, maybe we've found the first galaxy that formed in this area. But then I looked a little bit closer and realized this is right next to the previous galaxy that I showed you. So they're in the same place. This is probably a small galaxy that's falling in to this population 2 galaxy. So this is kind of saying, all right, maybe the simplest ideas aren't right. We've got population 3 galaxies forming out of the gas from the Big Bang right next to something that has already been through an earlier generation of star formation. As often happens in science, when you start to get good data, you realize your simple theories need to be made a little bit more complicated. So we've got a lot of work to do, and we are clearly making progress towards that initial goal of finding the first galaxies, which was thought of back in 1995 as what should the successor to the Hubble Space Telescope do? Find the first galaxies. We're well on our way. So this is one of the new science themes. Webb is making progress on its original science goals. We're doing good work. We're making progress. We haven't solved them all, but we are making progress. So moving on, another thing that's starting to emerge is we have a quiescent galaxy. This is a galaxy that has been through its first generation of stars and stopped forming galaxies. This was a bit of a surprise, only 730 megayears after the Big Bang, a redshift of 7.3. So this is an older stellar population that's used. When we see a quiescent galaxy, we think, okay, it's used up all of its gas, no longer forming stars, or perhaps there is a supermassive black hole in the center of this galaxy that has pushed out all of the gas and stopped the star formation from continuing to happen. We also see that some of these early galaxies are brighter than we were expecting by the model. And so here we have the galaxies fit up here, and the models are down here. Maybe a factor of 2 to 4 brighter than they should be. This was sometimes discussed in the press as a challenge to the Big Bang. Well, it's not a challenge to the Big Bang. It just means we don't quite understand how these galaxies initially form. Again, this is a theme. When we get more data, we have to make the theories a little bit more complicated. The universe is more efficient at forming galaxies early on, or forming stars in these galaxies early on than we expected. Our picture of how galaxies change over time is through interactions. These are relatively nearby galaxies, not the distant ones that I was showing you before, but as these 4 galaxies, 1, 2, 3, 4, are all at the same place, this is actually just right in the way, we have this galaxy is going through this galaxy, colliding with that, and the path in the middle, again, I need to show this for the people online, the path in the middle is are new stars that are forming through the collision of these galaxies. Now, this is a supercomputer simulation of 2 large galaxies colliding. And when galaxies collide, they don't go bang, the way cars collide, because most of a galaxy is empty space in between the stars. And it's very, very rare for stars to actually hit each other, for stars to collide. What does collide is the gas in between the stars, but the stars just kind of go slosh, and they interact with each other through gravity as the galaxies, the center of mass of the galaxies, pass through each other. In this collision of 2 large spiral galaxies, again simulated in a supercomputer because this actually takes place over several 100 million years, the spiral structure is all destroyed. We end up with something that looks a bit like an elliptical galaxy. And in this simulation, there are giant black holes in the center of each of these 2 galaxies. And those 2 giant black holes will eventually dissipate their energy and come to a collision which puts out a huge amount of energy in gravitational waves, which astronomers or physicists are just starting to be able to detect. This is a picture that we have of galaxy evolution, galaxies merging together and colliding with each other a whole lot. When they collide, they disrupt the structure, the spirals of the galaxies. But one of the things that we found in our early results with Webb is that galaxies do have structure much earlier than we thought. So this is a galaxy that is looking back in time 10.7 billion years, again compared to 13.8 billion years since the Big Bang, so about 3 billion years after the Big Bang, a redshift of 2.1. In the Hubble pictures on the left, you cannot see the spiral structure, but with Webb, the longer wavelengths, the bar in the center of this galaxy kind of jumps out at you. And this was a surprise to see this type of structure this early on in the history of galaxy evolution. And it's not the only one. We have these 6 galaxies, all have bars. This was a paper that came out about 6 months ago, and part of a project that I was working on. So this is our second theme, new science theme. Galaxy structure and evolution happened earlier than we thought. Stars were formed earlier in the galaxies, and the structures are forming earlier than we thought. Again, it's learning about the messy astrophysics. It's not addressing the cosmology or the fundamental physics, but this is an interesting theme that's emerging, and it's also very fortuitous because since the galaxies are brighter than we expected them to be, they're easier to see, easier to find. We can get better data on them, and so there's more to learn. Moving on to the formation of stars and their planets. This is a star-forming region called the Eagle Nebula in our own Milky Way, or sometimes called the Pillars of Creation, a very iconic image taken by the Hubble Space Telescope. And what's happening here is that this is in there is a very bright star up off the field of view right beyond the top, that is putting out a lot of ultraviolet light and a stellar wind blowing blowing gas towards this region. And in the very densest places, at the tips of these elephant trunks, are where the new stars are being formed. The less dense regions just get blown away, and that creates these pillars, which are basically shielded from the bright star at the top or beyond the top of the image. This is a visible light picture with Hubble. The dust absorbs the visible light, so it's dark. When we go to the near-infrared with Webb, we can start to see through that dust to where the stars are forming, the red objects right at the peak of those pillars. And then when we go to the mid-infrared, where the dust itself is emitting light, we can, again, map out the emission from the dust itself. With the advantage of an infrared space telescope is that we can see into where the stars and their planetary systems are forming. And this dust is the dust that will become part of the planets as the stars form. But we see this on a galactic scale as well. The Hubble picture of this nearby galaxy shows dark dust lanes, and when we go to the mid-infrared, those dust lanes start to glow in Webb images. But one thing we can see is that there are holes. It's not a smooth pattern. There are holes, bubbles being blown within the gas and the dust of the galaxies. This comes from bright stars, which, as I said, put out a lot of ultraviolet radiation and stellar winds, which blow bubbles. And as they do this, the process for star formation is that the biggest stars form first, form very quickly, burn the brightest, and die the quickest. It's a little bit counterintuitive, but the more fuel you put on a star, the quicker its lifetime is, because it just burns it that much faster. This blows a bubble in the surrounding gas, which does not allow additional star formation, but the edge of that bubble is the impact, the shock regions cause the collapse for the formation of smaller stars. And you can see this in this image where we have the bright star in the middle blowing a bubble and then the patchy regions around the outside. This is a picture of the Orion star-forming nebula, the Orion bar, and as we zoom in to this picture, we see a number of features that represent where stars are forming, but along the bar itself, there is a bright star up off the field of view of the image in the Orion trapezium up to the upper right. That is putting out this stellar wind, and the shock region is called a photodissociation region. And when we zoom in on that, we can see that in the ionized area that is being cleared out by the ultraviolet radiation of the star, we have a temperature of 10,000 degrees. Right on the edge, we have the atomic photodissociation region is 1,000 degrees, and where it is shielded, we have the molecular region, which is just 30 degrees. Very interactive process. Star formation is a messy process, and it's a self-interactive process. Here is one of our first images, again, a nursery of new stars and planets, and we can zoom in and find forming stars, stellar systems. Some of these stellar systems put out jets because, again, star formation is a messy process. And then when we do spectroscopy, we can see the rich chemistry of organic molecules. And taking a spectrum of a low-mass star, we see what was called a hydrocarbon factory. We have methane, and zooming out, we see acetylene, a whole bunch of different carbon and hydrogen molecules, a benzene ring there, the 6 carbon atoms all in a ring. We see carbon dioxide, hydrogen cyanide, and going out to methyl alcohols. So this is another one of Webb's new science themes. Star formation is a self-interactive process. We did know that before Webb, but Webb is allowing us to study that process, the interaction between the new stars that are forming and the next generation of stars that they trigger nearby. Moving on to the study of exoplanets, planets around other stars. It's been known for hundreds of years that it's a very valuable technique with astronomy to watch a planet go across the face of the sun. And early studies of transits of Venus and Mercury were used to determine the size of our solar system, the distance between the planets, and so forth. This video in the upper left demonstrates this using actual data, but not data of an exoplanet. This is a transit of the moon across the face of the sun. When viewed from the Earth, this is called a solar eclipse, and the size of the moon, the apparent size of the moon, is the apparent size of the sun. The moon blocks the sun, and we see the corona. But in fact, this video was not taken from the Earth. It was taken from one of our NASA satellites observing the sun and saw the moon transit across the face of the sun. But as a demonstration of what can happen when an exoplanet crosses in front of the sun, its star, when an exoplanet goes between its star and our telescope, is that light from the star, bright light from the star, can go through the atmosphere of the planet and reach our telescope. And we see the two together. We see just the total amount of light, but we can do the math of subtracting the light of the star blocked by the planet from the light of the star without the planet in front of it, and actually pull out the constituents of the atmosphere of the exoplanet. Transiting planets are fairly rare, but we've observed most of the sky to look for them, and we have now more than 1,000 candidates that Webb can observe. And one of the early results that Webb made was the first detection of carbon dioxide in the atmosphere of a gas giant planet around another star. We also have the first detection of sulfur dioxide on an exoplanet, shown here. And we followed a small rocky planet all the way around its orbit. So when it went in front of its star, we could see that dip in the total light. When it goes around the star, we see the transition from the nighttime side of the planet to the daytime side of the planet. When it goes behind the star, we just see the star without any light from the planet, and that sets the baseline. We can do all of the math and figure out the temperature of this planet. It was part of our search for small rocky planets like the Earth that have atmospheres, and ideally what we would want to see is a rocky planet with an atmosphere and a liquid ocean on the surface, which might have the conditions for life on other planets. We're not there yet. Webb is going to study enough of these small rocky planets until we find some with an atmosphere, but this one actually didn't have an atmosphere. It's too hot. So we're starting the process of studying planets around other stars. We have the first direct image of the planet separated from its star at 5 microns wavelength. And this is an emission spectrum that shows water, carbon dioxide, and even the presence of silicon clouds in the atmosphere of the exoplanet. So that takes us to the fourth of the new science themes. We are in the process of cataloging a wide diversity of exoplanets. I'll go pretty quickly through these highlights of the solar system. One of the things that we've done with Webb is to follow the occultation of a Kuiper belt object. This is a small icy body in the very outer solar system, and it has a ring around it. Many of the outer solar system bodies do have rings around, and as this star was passing behind the Kuiper belt object, we saw the diminution of the light from the star as it passed behind the ring. This ring is made of water ice, And we have also detected a main asteroid belt comet. So this is a icy body in the asteroid belt. Normally, comets come from the outer solar system and pass through the inner solar system and then go back out. But this is a comet that has perhaps been captured into the asteroid belt, where the asteroids are mostly made of rock. This is made of water, and the surprise of this observation was that they detected water in the comet, but not carbon dioxide, as they see in most similar types of objects. And then finally, in our solar system, we found a water geyser or a water volcano on the moon of Saturn Enceladus. And this was known that there were such things before, but Webb saw that it's much bigger than we thought, and had enough water emission to create a whole outer ring of Saturn that is the water that comes from the underground hidden ocean on Saturn's moon. And finally, when we look out in the outer solar system, Webb is very good at seeing water and very good at seeing icy rings, and these are the rings of the planet Uranus. So another theme is that we're following the water in the solar system. This is the water that was delivered to the Earth and formed the oceans on the Earth, came from the outer solar system. Now I'm going to take you through one last science result. This is a little bit complicated, but it shows that Webb is also addressing the biggest picture, the history of our universe, the fundamental parameters of our universe. When the ESA's Planck satellite measured light from just 300,000 years after the Big Bang, called the cosmic microwave background, it fit exquisitely to the data, and we use a model to relate those observations to the present day value of the expansion rate of the universe, called the Hubble constant. That measurement shows that the Hubble constant, as predicted from our measurements of the cosmic microwave background, was 67.4 plus or minus 0.5 in the units of kilometers per second per megaparsec. Recent results of the present day value of this number using a distance ladder, starting with geometrical distances to Cepheid variable stars, then using Cepheid variable stars in galaxies that have type 1a supernova, and then measuring type 1a supernova out in distant galaxies, measured this number to be 73 plus or minus 1. This is a discrepancy of 5 units of error, 5 sigma. That's often used to say this really is a difference. And this is not just two different measurements of the same thing. It's a measurement of the early universe, extrapolated using our model to the present day, compared to measurements of the present day. This discrepancy, the contribution that Webb made to this measurement was to be able to separate the Cepheid variable stars from their near neighbors with Webb, compared to Hubble, where they were blending together and they had to be pulled apart. But this difference is one of the big unexplained observations in our understanding of the universe. Webb has shown that it's not due to measurement error, and so we have to go to things like changes in our picture of the universe, possibly new physics, possibly it will give us understanding of the dark energy and the dark matter that govern the expansion of the universe. It's a very hot topic. There's been more than 1,000 papers written by theoretical physicists on this, trying to explain this. But the theme that we get from Webb is that there's still mysteries to solve, and there will still be mysteries even after Webb. So for the scientists in the audience, I wanted to point out that we have a special issue of the Publications of the Astronomical Society of the Pacific that gives a lot of the details of Webb instrumentation and technology. I encourage you to cite these papers when you use Webb in your research. Webb has had a big impact on the public. We had our pictures in Times Square and Piccadilly Circus. We had the front page of the New York Times twice in a row, 2 days in a row, also the Washington Post. And bands like Coldplay and Jimmy Buffett have used Webb imagery in their light shows. Webb was on the Google Doodle, and there's a US postage stamp with Webb. If you'd like to learn more about Webb, of course, we have a website, web.nasa.gov. We have a blog that takes things into a little bit more detail, blogs.nasa.gov/web. We have our image archive, webtelescope.org, and of course, you can follow us on social media. And we are constantly putting out new Webb pictures. This is a picture from last Thursday. It shows a forming star with putting out two jets, and it's actually just a beautiful picture, but it also tells us about the formation of stars and planetary systems. So I'd like to thank you all for coming. I apologize to those standing in the back, and I would be happy to take questions. Thank you.
Thanks a lot. I guess you can just moderate the questions. We have a microphone that's going to be passed around from the back. So please raise your hand and then wait for the microphone before asking your question.
I just wonder about the future of the Hubble telescope and if there's any gain if you would use both together.
Yeah, so the question is, what's the future of the Hubble Space Telescope, and do we use them together? The answer is yes and yes. Hubble has hopefully a long future. There are no more servicing missions. We're no longer flying the space shuttle, so we can't go there if anything stops working. But as long as Hubble keeps working, we will keep using Hubble to make astronomical observations. And scientists are thrilled to have both Hubble and Webb working together at the same time. Webb is the successor to Hubble. It's not the replacement. It's the next generation, but Hubble works in the ultraviolet light and visible light, a little bit into the near-infrared. Webb works in visible light, near-infrared, and mid-infrared. These are complementary. We get different data on the same thing. In the first year, most of the observations with Webb were pointed at things that Hubble had already looked at. And now, after the first year of observations, we're starting to see proposals coming to the Hubble Space Telescope to follow up the discoveries from Webb. So yeah, they work together well. That's true for all of the telescopes, both in space and on the ground. Astronomy is a multi-wavelength, multi-disciplinary subject, and observational astronomers love to have data of all different kinds on their favorite objects.
Yeah, thank you for the talk. It was very nice. And I have a, I think, more technical question. You said that you're doing like long exposure shots. Mm-hmm. How long is the exposure? And then the question is because the telescope is probably very fast, like some 20 or so kilometers per second or so, maybe. How do you, like if it's moving so fast and you have like a long exposure, how do you take the pictures without them getting super blurry?
Yeah, good questions. So first of all, we read out the detectors a lot. And while we are accumulating additional photons coming in, we still can read out the detectors without wiping out the signal. So we keep reading it out. It's called reading up the ramp. We see the signal to go up with time. We get more and more signal. And after about 1,000 seconds, typically, for an imaging observation, we do a destructive read and store those data and then start a new exposure. So when we observe something, say, for 100,000 seconds, we're actually making 100 images, and adding them together on the ground in the computer. And in fact, during those 1,000 seconds, we've read it out every 30 seconds, and we have all of those data as well. So that's a good question. There's not really any limit other than the fact that there's only so much time and there's so much to do with Webb. There's not really any limit to how long a total exposure we can do, but the limit on an individual readout is about 1,000 seconds. We also like to observe for 1,000 seconds in one place and then move a little bit. Because there are some gaps between the multiple detectors, and we want to fill in those gaps. So the other question, Webb is moving in its orbit very fast, as you said, about 30 kilometers per second. That sounds like it's really fast to us, but it's really far away. And what we do is we point the telescope at the target of interest, and we have a Gardner camera offset by a little bit, fraction of a degree, that finds a bright star and locks onto it and sends the signal. So the main imaging camera is not, we're not interpreting those data until later when they get to the ground. But on board, the Gardner will see whether that star moves out of its little box and send a signal to the control of the telescope to compensate. So that way we lock it on. And this is the same way that both Hubble works and ground-based telescopes work. We use a guide star to maintain position as there's any kind of drifts. The total time that Webb could stay pointed at one place in the sky is actually 10 days. After that, we would have to, we don't usually spend that long without doing something else, but that's the total time that we could potentially stay locked on without making adjustments.
Yes, I'm wondering, are you looking into galaxy formation within supervoids, or is that sort of a bit outside the domain of Webb? And also, how far back in time do you expect to be able to see galaxies? Perhaps you're dependent on using gravitational lensing.
So I didn't quite catch the first part of the question. You were asking about supervoids.
Yeah, are you going to use Webb to look at galaxy formation within supervoids?
Okay, so voids would be places where there's not a lot of material, and where you could try to look for formation in these rarefied environments. Most of the material on the large structures is still in large scales are still in structures like filaments and clusters of galaxies, and then in between there's not much there. Webb is a like Hubble is a small field of view instrument. It's designed to go very faint in a small part of the sky. We have a successor mission called the Roman Space Telescope, which will be launched in 2026. This is a mapper, and it has the sensitivity of Hubble. It's the size of Hubble, but it's got 100 times the field of view. So it can map large areas of the sky. That would probably be a better instrument to use to look for what happens in between the structures of galaxies. Although, in particular, if we know something's there, Webb can point at it and get good data on it. So the other question is how far back we can see in time with Webb. So I showed you the current record holder, light that was emitted just 325 million years after the Big Bang. That's about where we think probably the first galaxies formed, maybe as far back as 200. There's the Big Bang, the start of the universe. 200 million years, maybe we had the first stars and galaxies. 300 million. We have a number of candidates out at 400 million. So how far back we can see with Webb is determined by what's there, not by how far Webb can see. and also can we identify what we see. So this is what we built Webb to do. It's to find the first galaxies, the most distant galaxies that are there, not just that we can see, if you see the difference. So we might be in the right ballpark. We might be able to break that record a few times, going a little bit further back. But this is what we're doing. We're spending a lot of time with Webb to do this kind of science. Not only take the pictures, identify the candidates for the most distant galaxies, but then do that spectroscopy and find out what they're made up of and their characteristics and how old are they in particular, and do we have to keep working. And the other thing is that, reality is always more complicated than your simplest theories. There might be some diversity within these galaxies. They might not all be the same. So we'll keep going probably for the lifetime of Webb on this science, on studying the very early universe.
This is no longer on. I think that's a hint. We have to wrap it up. But thank you so much again. Wonderful talk.
Thank you very much for coming. Thank you.